I want you to imagine that you are an angry young man. Why are you an angry young man? Well, because you have flippers for arms. And what does an angry young man do? He gets himself a horse. Is he nice to the horse? Of course he's not nice to the horse. He's an angry young man. But what does he do with the horse? Well, he robs a bank. So I want you to imagine that you are an angry young man with flippers for arms, riding a horse that you are not nice to, and you go and you ride a bank. Or you ride a bank? You go and you rob a bank. After you rob the bank, you turn around and you go back home with your winnings. When you get back home, you fall in love with the horse. The horse says, "You know, Andrew, I think you're better than this." And so you return as quickly as you can to the bank to return the money. The story of our angry young man is a story of motion as we watch him move forward and backwards. So let me tell you a little bit about that motion. Let's begin here. We're going to define a function called d of t, and d of t is going to be his displacement from home. And let's say that it's going to be measured in units of miles, so that this variable right here would be the hours that have passed. And then this right here would be the number of miles that our angry young man is from home. And let's suppose that this point, 1, 2, 3, 4, 5, 6, 7, 8, this point, this point, this point, and this point are on our graph, and it's smooth so that it looks something like that. He's at home when his displacement is 0, and he's at the bank when his displacement is 8, and he's the furthest away from when he started. Now, here's what I want you to figure out. Our angry young man, when is he speeding up and when is he slowing down on his journey? And in order to figure out when he is speeding up and when he is slowing down, we're going to need to know some other quantities. So let's talk about those. The first is something called the velocity. Velocity is defined as the rate of change of displacement. And so if this is the rate of change of his displacement, it has units, and those units are easy to calculate. We know that all rates of change are change in y over change in x. So y is the displacement that was measured in miles, and t is the time that was measured in hours. So our velocity will be measured in, can I spell? Miles per hour. Okay. If he is moving to the right, then he has a positive velocity. If he is moving to the left, he has a negative velocity. Velocity can be positive or negative. The next quantity we need to know about is something that I'm going to call a of t, which represents the acceleration. Now, when you're in your car and you press on the accelerator, you can't see my foot, but I'm pushing on the accelerator. When you push on the accelerator, what does it do to the velocity of your car? It makes it go up. It changes the velocity. So acceleration is the rate of change of velocity. It also has units. Since now we're looking at how the velocity changes as time goes by, we would say that in the numerator, our units are the units of velocity. The units of velocity were miles per hour, And then in the denominator, we have hours. Hey, so that kind of makes sense, right? If you're looking at how velocity is changing, you're looking at how much the miles per hour go up every hour. Acceleration can also be positive or negative, right? If we see the velocity increasing, then we have a positive acceleration. If we see the velocity decreasing, then we have a negative acceleration. The last quantity we need to talk about is the one that I said is our goal. We want to figure out when our angry young man is speeding up and when he is slowing down. So we need to know a little bit about speed. Speed is closely related to velocity. Here's the difference. Speed is always positive. Velocity could be positive or negative. So speed is defined as the absolute value of the velocity. And it will always have the same units as the velocity. So with that in mind, I want you to draw pictures of the speed, the acceleration, and the velocity based on this displacement graph that we have right here. Let's start by doing the velocity together. So what I see here is increasing, decreasing, increasing, which means that he was moving to the right, and then he was moving to the left, and then he was moving to the right again, which means that there were 2 points on here where he was not moving, here at the maximum and here at the minimum. So if we wanted to draw the velocity, we could say, I know that at these 2 instances, at time 1 hour and at time 3 hours, his velocity is 0. Boom, boom. When he is moving to the right, we have a positive slope, which means that we have a positive velocity because the velocity is the derivative of the graph that we have up here. It's the derivative of the displacement. So our graph, I'm not going to get too picky about it, but we know it's going to be positive and then negative because displacement is decreasing, and then positive because displacement is increasing. So our graph should look something like that. So there's our velocity graph. Let's use that velocity graph to draw the acceleration. Acceleration is the derivative of the velocity, which means that it is also the second derivative of the displacement. Now, the way that we're going to draw it is to look right here. Okay, that's where the velocity is at a minimum, and it has a horizontal rate of change. Okay, which means that down here on the acceleration graph, we're going to have a 0. So when our velocity hits a minimum, our acceleration is at 0. And I think it's worth noting, if we look up here, that on the original graph, that is associated with this point right here, which is the point of inflection. So the point of inflection on a displacement graph will be associated with when the acceleration is 0. Now, to draw the rest of this graph, we would say velocity decreasing, velocity increasing. Therefore, velocity or acceleration negative, acceleration positive. Once again, decreasing, increasing, so negative, positive. Our graph's going to look something like that. This brings me finally to the speed. Now, to draw the speed, we're going to do something different. Where'd my paper go? Here you are. We know that speed is the absolute value of velocity. And so what we could do to draw this graph is say, all right, here's our velocity graph. This is parchment paper. You don't have to do this. You can just watch me. But I'm going to draw the velocity graph. Now, I'll notice that the velocity has these two places where it's positive, and then this area in the middle where it's negative. We want the speed to be always positive. So what we need to do is take the negative components right here and take their absolute value. The way you do that is just by flipping it over the x-axis. Now everything is on the positive side of the x-axis, and our velocity graph is going to look something like this. Boom, boom. Boom, boom. Boom, boom. Which brings us to the answer to our question, which is, when is our angry young man speeding up? Well, he's speeding up when the speed is increasing. Look at the speed graph. It's increasing right here and right here. This brings me to the big idea for today. Ordinarily, you do not want to have to draw all of these graphs. It's a pain in the tuchus. So it would be nice if there was a simpler way to identify when an object like an angry young man is speeding up. And I'll tell you that it's doable. Now, we know that the answer is from 1 to 2 and from 3 to 4. We got that from the speed graph. So I'm going to mark that right here, that those are the two intervals where we are speeding up. And let's see, can we use the velocity to identify when it's speeding up? Well, velocity is positive here, negative here, negative here, and positive here. So is there like a one-to-one relationship between where we are speeding up and the velocity? The answer is no. Hang on, my phone is ringing. Hello, may I help you? They're offering me a cancer screening. I'm gonna pass. Where were we? All right, so let's see. So we figured out that the velocities will not tell us where it's speeding up. What about the accelerations? The acceleration goes negative, negative, positive, positive. So negative, negative, positive, positive. Most people think that the acceleration will tell you where it's speeding up. It's actually not the case. Look at it, because there is not a clear relationship between the speeding up regions and the accelerations. However, there is a relationship if you look at both the velocity and the acceleration at the same time. Can you tell me what that relationship is for the two regions where it is speeding up? That's right. A particle, or an angry young man, is speeding up when the velocity and the acceleration have the same sign. Okay. And on this interval here, and on this interval here, where they have opposite signs, the particle, or an angry young man in this case, will be slowing down. So there it is, ladies and gentlemen. We've figured out when an object is speeding up and slowing down. We have taken this angry young man, and we have made him so happy. The end.